The optimization tool is a graphical user interface that allows you to quickly set up, run, and evaluate your optimization problems. I will show you how to set up and run an example optimization problem using the new Optim Tool graphical user interface. I can open the optimization tool by typing Optim Tool at the MATLAB command prompt. From the optimization tool, I can define, solve, and assess my optimization problems. I can select the solver that applies to my problem type, choose an algorithm, define my problem and constraints, as well as start, pause, stop the solver, view the status and results as the solver runs. Once I have selected a solver, I can view or modify a variety of options, including the stopping criteria, algorithm settings, and a variety of other options that you can see here. You can quickly learn about all of these options in the optional quick reference panel that is part of the optimization tool. One of the nice features of the optimization tool is that it provides a link between the solver and the options available for that solver. Notice that when I change the solver to an unconstrained solver, that the optimization tool updates to the appropriate input and options available for the solver selected. You can see that the problem definition input has changed. The constraint section is no longer available. The algorithm settings have been disabled, and the quick reference panel displays content associated with the selected solver. I will demonstrate the Optim Tool GUI using an example problem. I want to minimize the weight of a spring used in an automotive valve subject to several linear and nonlinear constraints as shown here. Two design parameters that can be modified are shown here as big D, the coil diameter, and little d, the wire diameter. Constraints on spring geometry and operation are listed here for reference. The curly brackets denote that the constraint is a function of the expression included inside the brackets. I will now set up and solve this problem using the optimization tool. I'll start by selecting a solver. From the solver menu, you can see that I have a variety of solvers to choose from. Each solver listed here addresses a different optimization problem type. The spring problem is a nonlinear constraint minimization problem. The fmin-con solver addresses this type of problem, so I'll select it. The large-scale algorithm is useful for problems that have structure or use sparse matrices. My spring problem does not require a large-scale algorithm, so I'll select the medium scale. The function that calculates the spring weight is defined in an M file named springObjective. This is the objective function, and I'll open it now to view its contents. The function accepts two inputs, big D and little d, as a vector defined by x. And it returns the spring weight as the output y. I'll define the objective function as a function handle, which is the required format. I'll set an initial start point of 1.0 for big D and 0.2 for little d. The lower bounds for this problem are 0.1 for big D and 0.01 for little d. The constraints are defined in a function named springConstraints using a format similar to the objective function. This function contains all the constraints shown earlier. I'll enter the function name in the nonlinear constraint field. My problem is now set up. I could start the solver by clicking on the Start button, and the solver would execute using the default options. However, I want to change some of the default options to get more information about the solution progress as the solver executes. I'm going to enable plotting under the plot functions to enable viewing of the spring weight and the current value of big D and little d as the solver iterates. I'm done setting up my problem, and I will start the solver now. You can see that the solver begins to iterate and the plots that I requested are shown. The bottom plot shows the iteration history for the spring weight. The top plot shows the current value of big D and little d and is updated after each iteration. This plot allows me to quickly see if the solver is progressing towards a realistic solution to my problem. If I determine that the solution progress is not running as expected, I can stop the execution of the solver from within the plot rather than wait for the solver to terminate on its own. The final results are shown in the status window. The values of big D and little d that satisfy my problem definition and constraints are 1.129 and 0.138. The final spring weight is shown here as 0.0448. After finishing my optimization, I can export my results and problem formulation to the MATLAB workspace, where I can perform additional analysis or save my work for later use. I can also automatically generate an M file from my session. This is useful for preserving my work or including it in other analyses or applications. I will capture my problem as an M file. I will name it Spring Optim. You can see that the Optim tool generates clearly commented code that captures the work I did. In summary, I was able to quickly set up and run my optimization problem using the new optimization tool GUI. I showed you how to use the Optim tool to set up an optimization problem, modify solver options, run the solver, view results, and capture your work as an M file. This concludes the Optim tool demo. You can close this window now or replay this demonstration using the controls displayed below.